Hi everyone. So today we're going to look at the basics of the Laplace transform, and you saw a little bit of it already. Hopefully by the end of this session you should be able to take some functions from the time domain and put them into the Laplace domain by applying the integral functions. And you should also be able to use the Laplace tables, where you could just directly look at a function and then say what the Laplace transform is. So what is the Laplace transform? In essence, it is a transformation from a derivative space to an algebraic space. And this means instead of solving differential equations, you have to solve algebraic ones. And this is important because when you did the first and second order circuits, we were solving differential equations. So you could see if the circuits get very complex, you could have a very difficult time if you have a lot of nodes and you have to reduce all to single differential equations. Whereas if you take it to the Laplace domain, you could essentially work with those as though they're DC circuits. So the same way you go about your nodal analysis and your loop analysis and so on, you could do that same sort of analysis with in the Laplace domain, even though you were looking at the transients. And then you could, when you solve it for whatever voltage or current you want, you can simply bring it back to the time domain. So as we saw before, the Laplace domain is where you take a function of t, you apply the Laplace transform, and you end up with a function of s. So here you have a function of t with a common f, and here we have the capital F for the function of s. And all we do to go from one to the other is we go through this integral, f of t e to the minus st dt. And since we're integrating with respect to t and we have limits, all the t's are going to disappear, and what we're going to remain with are functions of s. And similarly, we have the Laplace, the inverse transform, where we take a function of s and we end up with a function of t. And here we do the opposite. We differentiate with respect to s, and then because we have the limits, all the s's are going to disappear and leave you with the t's. So as I mentioned before, we'll take our problem, in our case it will be circuits. We'll transform the circuit from the time domain into the Laplace domain, and then we are going to solve it using our nodal analysis or loop analysis or superposition or whatever technique that we want to use, and then we're going to take it back into the time domain. So before we get into that, we're going to look in this session at just some common transform pairs. So if we have a constant as our function, f of t is equal to k, then f of s is the integral between 0 and infinity, k e to the minus st dt. When we go through that integration, and you could go through it for yourself, it's not a difficult thing to do, you will see that we end up with k on s. So if we move on to a pulse function, the pulse function is where we have between t1 and t2 we have some we have the value of k, and before and after that it is 0. So we have between 0 and t1 we have 0 for t less than t1. For t less than t2 but greater than t1, which is this red section here, it is equal to k, and then again above t2 it is equal to 0. So I could split that into three integrals of constants, and then the first and the last will be 0 since the constant is 0, and the middle one I will end up with this part here, which I could simplify to this. So I have e to the minus st1 e to the minus st2. Now, one common variation of this, one specific instance of a pulse function, is what we call a unit step function. And in the unit step function, we take t1 to 0 and we take t2 to infinity. So what we end up with is at t equals 0, we have a step. That's why we call it a unit step. K in the unit step function is equal to 1. So if I substitute those things, k is 1, t1 is 0, t2 is infinity, then what I'll get is 1, in this case k should be 1, for the unit step, 1 on s, u of t is 1 for t greater than or equal to 0. Then if I take this to the Laplace domain, I will get 1 on s. And we could sometimes model switches closing as step functions. Sometimes, not in all cases. Only in very specific instances, but it is something we will do for basic circuits that we are going to look at. So just to look at some other functions, you could go through these by yourself and see what you get. K e to the 8t, and you could pause the video and work through the integration and make sure you understand it. It doesn't make sense me just reading everything here on the slide. So go through it, make sure you understand it, make sure you end up with the result. When you're finished with that, you could go to the cosine function. Now here, what we typically do is we change it into its exponential form to make it easier to integrate, since we're multiplying by e to the minus st. And out of that, you should get this transform here. Now you might think, well, this seems more difficult. Why would I go through all of these integrations? What is the point of having the transform if in order to get the transform to make the solving a differential equation easier, I have to do all of this integration? It's the same amount of work. So luckily we don't have to go through all the integrations each time. You'll see that we have transform pair tables up, and you could Google them. If you just Google Laplace transform table, you should get them. And this is what we're really going to use. We're going to use these tables which tell us for a particular function what the transform is. We're going to use that to simply go back and forth between the Laplace domain and the time domain. So we are not going to go through this process of integration each time. And actually, we're not going to go through it at all. You have a course on Laplace transform next year where you'll do that in a lot more depth. For this course, the important thing is to know how to use the transform tables. Of course, you also need to know what the transform is, but don't spend too much time just trying to integrate a whole set of different functions. The important thing is to learn to use the tables. So, the ones we did already, u of t, e to the minus at, and cosine bt. So you'll see that if you look in the transform tables here, you just see it directly. You have u of t, it tells you what the transform is in the Laplace domain. E to the minus at, t, n on n factorial. So all these functions. So now the natural question is, well, what happens if I don't have one of these functions? Well, you could probably synthesize your function from some combination of these. This will cover a really large range of functions if you take these and you could put them in any combination. But how do you do that? Because the table does not tell you how to combine these functions. But so to do that, what you have to do is actually just look at the next table, which tells you how to modify your transforms. So if you have f of t and you want to multiply it by a, so if you had u of t but as your function, which is your unit step, but you don't have it at 1, what if you had it at 3 instead of 1? Then what this is, if this is u of t, this is 3 u of t. So it represents a magnitude scaling. So here I would just look in my table and see a f of t, then I just multiply a f of s. So if u of s, I should use a capital here, is equal to 1 on s, then if I have 3 u of t, then I would get 3 u of s, which is 3 on s. So let's look at a little more complex example. So I have f of t is equal to t, and if I look in my original direct transform, I will see that that corresponds to 1 on s. Sorry, to 1 on s squared. So I have f of t is equal to t. I look at my table and I see t will transform to 1 on s squared. If I want to change that and I want to get the function for at, what is the transform for at? That represents a time scaling. So then I have to look at, instead of going back and doing a whole integration because I can't find it in my original table. So for example, I can't find at in this table. It doesn't mean I have to go and do a whole new integration. What I do is I simply look in my I look in my modified table and I see f of at, and then it tells me how to modify my Laplace function. So my Laplace function is 1 on s squared. Now I have to modify that by multiplying by 1 on a, and then I have s on a replacing the s. So instead of 1 on s squared, I'll get 1 on s over a squared. If I wanted e to the minus at f of t, which is t e to the minus at, again I look at my transform, my modified transform, and I'll see e to the minus at f of t, which is a frequency shift, will be f of s plus a. So I have my original transform, which is 1 on s squared, and when I multiply it by e to the minus at, the s from the f of s simply becomes s plus a. So I have 1 on s plus a squared. So I would like you to go through some examples, firstly with the forward transform. So you have some functions in t, and you could look at what is your base function, what is the transformation that undergoes, and then how to use the tables in order to get them. So I'd like you to do that for these two examples here, and then go the opposite way with the inverse transform. And for these cases, you'll see we have denominators here which are factored out. I've factored them out for you. So what you need to do is you have to take these functions and transform them into forms that you could find in the tables. So for example, you know that there is a form here which is 1 on s plus a. So 1 on s plus a will transform to e to the minus at. So if I go back to these examples, I could take this and I could turn it into a over s plus 2 plus b over s plus 6. And then once I have this, this will transform into a e to the minus 2t plus b e to the minus 6t. So you have to essentially break this up into the constituent parts that you could find in the table, and then you can directly use the table to find what the time domain functions are. Right? And I typically do this using comparing coefficients. So to summarize, you should be able to take a function in the time domain and integrate it, simple functions at least, as long as you know how to integrate the function, and integrate it to get what the Laplace integral function is, and you should be able to use the tables of transform pairs and modified transforms to construct transforms of complex functions by looking at simple ones and how they change using the modified tables. Next time, what we're going to look at is how circuits are represented in the Laplace domain. So how do we use these Laplace transformations to make our circuit analysis easier?